Hello everyone. So here in this problem f of x comma y and phi of x comma y are homogeneous functions of x and y of degree p and q respectively, and u is given as f plus phi, and we have to show that 1 upon p into p minus q in bracket x square dou square u by dou x square plus 2xy dou square u by dou x dou y plus y square dou square u by dou y square bracket complete minus q minus 1 upon p minus q into x dou u by dou x plus y dou u by dou y bracket complete is equal to f of x comma y. So it's very small question, is it? No. So the number of terms are more, and hence to solve this we are going to use a shortcut method, which is obviously by using the Euler's theorem, because here in the question it is given that the given functions are homogeneous functions, and for all homogeneous functions we can apply the Euler's theorem. So since these two functions are homogeneous functions, we'll apply the Euler's theorem for both of them. So here I'll say, since f and phi are homogeneous functions of degree p and q respectively, so by Euler's theorem we can say that x dou f by dou x plus y dou f by dou y is equal to pf, because the degree is p, and second is x dou phi by dou x plus y dou phi by dou y is equal to q phi. So I'll say this as equation number 1 and this as equation number 2. So we got two equations from Euler's theorem. Now also u is given as f plus phi. So here I'll say also u is equal to f plus phi. So therefore here we can get dou u by dou x as dou f by dou x plus dou phi by dou x, and dou u by dou y as dou f by dou y plus dou phi by dou y. Now what we can do is, here in the proof if you'll observe, then we want x dou u by dou x plus y dou u by dou y, and to get that we'll add equation number 1 and 2. So when we'll add equation 1 and 2, on the left hand side we can take x common and we'll get dou f by dou x plus dou phi by dou x inside the bracket. So here we'll say, therefore adding equation number 1 and 2, so we'll get x in bracket dou f by dou x plus dou phi by dou x plus, now here we can take y common, we'll get dou f by dou y plus dou phi by dou y in the bracket. So y common dou f by dou y plus dou phi by dou y in the bracket is equal to, on the right hand side we have p f and q phi, so that is p f plus q phi. Now if you'll observe here, then the value of this bracket is dou u by dou x, so therefore we will get x dou u by dou x plus y dou u by dou y is equal to p f plus q phi, and I'll say this as equation number 3. Now we got this bracket. Now to get this bracket we have to apply the corollary of Euler's theorem. So since these two functions are homogeneous functions, we can apply the corollary of Euler's theorem for both these functions. So here I'll say, therefore by corollary of Euler's theorem we will get For f we will get x square dou square f by dou x square plus 2xy dou square f by dou x dou y plus y square dou square f by dou y square is equal to n minus 1 into f. So here n is degree and the degree of this function f is p. So this will become p into p minus 1 into f, and I'll say this as equation number 4. Now by applying the same corollary for phi we will get, so therefore x square dou square phi by dou x square plus 2xy dou square phi by dou x dou y plus y square dou square phi by dou y square is equal to, the degree is q, so q minus 1 into phi. We'll say this as equation number 5. After that, to get the bracket term we have to add equation number 4 and 5. So here I'll say therefore adding equation number 4 and 5. So in equation number 4 and 5, if you'll observe the first term, then here the first term is x square dou square phi by dou x square, and here the first term is x square dou square f by dou x square. So from both these terms we can take x square common. So we'll get x square common. Inside bracket we'll get dou square phi by dou x square and dou square f by dou x square, and I'm writing it over here. We are getting dou square f by dou x square plus dou square phi by dou x square. Now to get the value of this function, we'll again make use of this u equal to f plus q. So if we'll differentiate this whole equation twice partially with respect to x, then here we'll get dou square u by dou x square. So I am partially differentiating u with respect to x twice. Similarly on right hand side we'll get dou square f by dou x square and dou square phi by dou x square. It means the value of this is dou square u by dou x square. So after taking x square common, the addition of these two terms can be dou square u by dou x square plus, now observe the second term, here the 2xy and here 2xy we can take common. So 2xy outside. Again here in the bracket we'll get dou square phi by dou x dou y and dou square f by dou x dou y. So addition of this is nothing but dou square u by dou x dou y. So here we'll say it is equal to dou square u by dou x dou y plus, now third term, here it is y square and here it is y square, we can take common. So y square outside, and in the bracket we have dou square phi by dou y square plus dou square f by dou y square, which is again dou square u by dou y square. So we'll get dou square u by dou y square. Next we'll add the right hand side. In right hand side we'll get p into p minus 1 into f plus q into q minus 1 into phi. So p into p minus 1 into f plus q into q minus 1 into phi. This is continuation of problem number 2 based on corollary 1 of Euler's theorem. So now here we got the value of x square dou square u by dou x square plus 2xy dou square u by dou x dou y plus y square dou square u by dou y square, and I will say this as equation number 6. So now if we will see the required proof, then we got value of this bracket and we got value of this bracket. So we have to multiply the value of this bracket with 1 upon p into p minus q and the value of this bracket with q minus 1 upon p into p minus q, and then we have to subtract these two values. So the value of this bracket is our equation number 6 and the value of this bracket is our equation number 3. So we will multiply equation number 6 with 1 upon p into p minus q and equation number 3 with this term, and then we will subtract. So here I will say therefore 1 upon p into p minus q into equation number 6 minus q upon or q minus 1 upon p into p minus q into equation number 3. So by doing this we will get the required left hand side. So we will solve the right hand side now. So here I will say, so therefore the left hand side will be as it is. So I will say therefore required LHS I will get. So we will get that term. Now we will solve the right hand side to get the answer as f of x comma y. So as we have multiplied the equation number 6 with 1 upon p into p minus q, so we have to multiply that equation number 6 on both sides. So after multiplying left hand side we got this term. After multiplying right hand side we will get 1 upon p into p minus q inside the bracket, here p into p minus 1 into f plus q into q minus 1 into phi. Again minus q minus 1 upon p into p minus q into right hand side of equation number 3. So here the right hand side of 3 is pf plus q phi. So here in the bracket we will get pf plus q phi. So now we will take this 1 upon p into p minus q common from both these terms. So from here 1 upon p minus q, 1 upon p into p minus q, and here 1 upon p into p minus q. So here the right hand side will be 1 upon p into p minus q, that we are taking common. So inside bracket we will get this bracket as it is because we have taken this term as common. So I will just copy it down. So p into p minus 1 into f plus q into q minus 1 into phi. Now we have taken 1 upon p into p minus q common from second term also. So after taking it common, here this bracket will remain and minus of q minus 1 will remain. So I will send this minus of q minus 1 inside the bracket, it will multiply each term. So from here we will get minus of p into q minus 1 f and minus of q into q minus 1 into phi. So after this, if we will observe, then the second and third term is same and opposite in sign, so we can cancel it, that is plus q into q minus 1 phi and minus q into q minus 1 phi. So therefore we will get right hand side as 1 upon p into p minus q. In the bracket we will get, this is p square minus p, and from here we will get minus pq plus p, and the f is common. Now again we can cancel this plus p and minus p, and from these two terms we can take p common. So 1 upon p into p minus q as it is. By taking p common, in the bracket we will get p from here minus we will get q from here into f. So from here also we can cancel p and p, and p minus q, p minus q. So we will get f in this case. So that means we will get function of x and y. So here as we want the right hand side is f of x comma y, we have proved that we are getting the right hand side as f of x comma y. Thank you.